All right, we're recording, and we have an Eagles win in our midst, 22-21.
And
That's how we do it.
very good run by Daniel Jones. Very, very nicely done.
Yeah,
I
it's a good
save
day.
that as a video in my phone so I can play that whenever I want to.
Okay, so let's go ahead and share our screen here. We are continuing the lesson that was previously watched in the video that introduced Mr. Ostrander to you, if you hadn't already met him or seen him. I hope that was mildly entertaining. He's a funny guy. But we've learned to complete the square in equations with the intention to solve. But we also want to utilize completing the square with the intention to graph. And we've been given a problem here that is already in a vertex form for a parabola. Can you talk to the students about what vertex form is, Mrs. Contreras?
Yeah, because vertex form is, well, it's not standard form where we have ax squared plus bx plus c. That's standard form. And it's not factored form where we have, like, if it's factorable, then we have like x minus one of the roots times x minus the other of the roots, because those are other forms of parabolas. Just like how we have point slope form for equations for lines, and we also have slope intercept form, and we also have, is it called standard form that we use like when we're thinking about like vectors and stuff?
Yeah, ax plus by plus c.
Yeah. So just like that for lines, we also have different forms for parabolas, and vertex form is nice because we can see where the vertex is going to be. Because remember, think back to all the transformations that we did, where we had vertical shifts and we had horizontal shifts.
I wonder if they can see me.
You're gonna.
Yeah, well, I think I might. I'm a parabola.
Mr. Kirk is a parabola. So then, if it's like the regular parent function parabola and then plus like 7, then it's going to shift up. So then the vertex is going to be at 0, 7. But if it's like x minus 3 quantity squared plus 7 or something like that, then the vertex would shift to 3, 7.
I'm a crab. I've shifted 3 to maybe the right direction, maybe the wrong direction. I don't actually know because my screen I think is flipped.
The mirrored thing.
And then I go up 7.
Okay, I think you moved left in my view, but
in my view I did it right. I promise.
Okay.
I'm also talking so that I know my screen's being highlighted. All right. This is we can also call this crab form.
Crab elevator form.
Crab elevator form. Imagine a crab entering an elevator. That's the shift. And then the elevator applying acceleration. Physics is involved. I'm crossing this off because we don't want you to think about it this way. We want you to just understand. Yeah. So we're in vertex form. A x minus h squared plus k. That a, it's just a dilation. It's not actually affecting its vertex. Cool. So we are in vertex form over here on the left, right? Our goal of today is to be able to turn things into vertex form if given one of these other forms. What's our vertex?
Our vertex is 3, 5.
Not negative 3, 5?
No, because remember when our shifts are happening, they're going kind of like in the opposite direction because that's how our domain is changing.
Yeah, that value h, I'll just give my perspective real quick after yours. That value h is the positive number that you're subtracting. We are subtracting the value 3. That is what our horizontal coordinate is. Okay, it's just the same. 3, 5. Boom. What are some of the properties of this graph?
It is an upward-facing parabola.
I see what you did there. We got a red crab. Go Blazers. We should change our mascot from the Blazer, which I'm not a big fan of, to a crab.
Yeah, that would be pretty cool.
That'd be better.
Although crabs aren't red unless they're cooked. So maybe we would also need to change Blair's color to
blue crab.
Blue, yeah. But then, like
spring
break is already blue.
We digress. Our goal is to make this video not super long. All right, so what were you saying?
upward facing parabola, there's no vertical dilation, no horizontal dilation, so we get points where we want them, like 1 up, and then, 3 up from there as we're going.
Yeah, I just kind of like think about this as my new origin and then graph what I've graphed 1,000 billion times. 1,000 billion, that's a trillion. Cool, there it is. So talk to me about these properties.
The domain is all real numbers.
Let me actually zoom out a little bit so we can, the
there
domain's
you go.
all real numbers.
Domain's all real numbers. The range starts at 5 and then goes up to infinity. It includes 5. Indeed. We established that increasing and decreasing intervals have to be open. So we're going increasing from 3 to infinity and decreasing from negative infinity to 3. In terms of x-intercepts, are we ever going to cross the x-axis? Because the x-axis is where y equals 0, and that's outside of our range. So
it's kind of like when I say find the x, this is my little thought on this topic. All right, you said this in a previous video, but when we want to find the x-intercepts, we need to figure out when the equation that we've been given, the function that we've been given, x minus 3 squared plus 5, and the line 0, the horizontal line 0, intersect. We talked about this when we were thinking about the solutions to the problems up here that we did with Mr. Ostrander when we were graphing things. This one was, when is x squared and the line y equals 9 intersect? When does the line y equals 0, which I've drawn here, and the function that we've been given intersect? And that's never, right?
Never.
Nada.
Is that what we're supposed to say, or not applicable, or does not exist? Like, what should we say there?
I'm cool with all three of those. You?
Yeah. You could write the shrug guy, I guess, just not on test.
I don't know how to draw the shrug guy. That looks like a bat. Moose. That looks like that Pokemon with like the
Woobat?
Yeah, Woobat. Yeah, it looks like Woobat. The answer to this is not Woobat. It's I'm gonna put NA so we can move on. We have a goal to be efficient today. Y-intercept.
Y-intercept is where we cross the y-axis, which is when x equals 0. So I think what we can do is just plug into our function 0.
And then we get 9 plus 5.
9 plus 5 is 14.
Boom. I'm going to write y equals 14. But I guess the y-intercept, that's a coordinate. I'll put the coordinate 0, 14.
Sounds good.
This one definitely happens because you claimed the domain is all real numbers. So there is a value at x equals 0.
There must exist
a
value. Yeah.
Asymptotes.
Dinna. Or na. N/a. Not applicable.
Yes. It looks like maybe there's a vertical asymptote, but there's definitely not because there is a value at that point.
Because our domain is all real numbers.
There you go. So that's a better way to think about it, I think. Bounded.
It's bounded below.
No, let's write that. All right, because the word bounded, if I say, is this bounded? The answer would actually be no, right?
Correct.
Because this is not. Yeah.
Yeah, because bounded means that you need bounded below and bounded above. So you need to have this like bounded sandwich. But since we don't have the bounded sandwich, we can't just say it's bounded, but we can specify that it's bounded below because the range that we have is from 5 to 8. Not 5 to 8. 5 to sideways
5
8.
to sideways 8. Yeah.
5 to infinity.
This is bounded by the value 4, 3, 2, negative 6,724,
negative
etc.
a trillion.
Yeah, negative 1,000 billions, right? End behavior. As
X
it's
mole day. Happy mole day. I forgot.
Ooh, what is mole? It's 6. You know, it's
Avogadro's number.
Well, yeah, but
like
what
avocado's number.
What
Something
is it?
times 10 to the 3rd.
I think it's 23rd. I think it's a really big number.
10 to the 23rd.
Yeah,
because it's 1023. That's why it's mole. Yeah.
Oh, so it's Okay. But end behavior as X approaches. I've been asked many times in class now. What does this arrow mean?
Approaches. Indeed.
Approaches is one way to think about it. Indeed, let it be so.
It is also it's drawing your mind to what we talked about with limits.
Mm-hmm.
The limit as x approaches negative infinity of our function is positive infinity.
Boom, that's where it's going. And similarly with infinity, this is the same end behavior. We can talk about this being the end behavior.
End behavior.
End behavior. And then last but not least, extrema.
Extrema, we have a absolute minimum of 5.
All right, and we don't need to justify it here. That's not what we're asking you to do. You've done that. That's in your pocket. You know the definitions. But does it exist? Yes, 5. If you were to justify it, you would need an interval around it. Marks, that would be for relative min. This is an absolute min. It's the lowest point on the domain. All right, let's proceed and actually do the goal of today. And that's turn something into vertex form. Do what we just did, but with something that's a little bit less obvious. And I'm going to zoom back in.
Okay.
For this full width. Were you going to say that?
Yep.
Cool. F of x is equal to x squared minus 12x plus 38. How can we turn this thing into vertex form?
Well, we need to find, effectively, we need a perfect square trinomial and something else.
Okay.
So what I'm seeing is we have a leading coefficient of 1, so that's nice. And then we have negative 12 as our like b term. So what we need to do, I think, is figure out how to make negative 12x part of a perfect square trinomial. And I think we'll get negative 12 when we add negative 6 and negative 6.
So yeah, negative 6 plus negative 6. Those are the two things that are going to add to negative 12.
So
which
then
is
we
half
multiply
of 12.
those, which is half of 12.
Uh-huh.
And so we should have x squared minus 12x plus 36. But right now we have plus 38. So we could do a couple of things.
All right. I have opinions about this, but I know you do too. What do you want to do?
Well, I just feel lazy and I don't feel like writing extra things. Mm-hmm. So the way that I would say we could do this is have x squared minus 12x. Oh, you're writing too. Whoops. Okay.
Oh no. Oh, that's kind of cool. Let me back up. I'm sorry. Let's have you write this one.
Okay. And then plus 36, which is close to 38, but not quite. So what do we need to add to 36? Well, we can add 2. And so now we have a perfect square trinomial of x minus 6 quantity squared. And that's going to be this first part. And then we have plus 2. It's all going to appear. There it is. So then we found our vertex form. But what would you want to do, Mr. Kirk?
Well, so let me do this. Let me just say f of x. Boom. Because we never altered the left-hand side, right?
Correct.
I want to make that clear. And when Mr. Oshana was doing this earlier, it was equations. You can alter both sides as long as you do the same thing to one side as you do to the other. He forgot to do that at the beginning. Let's just call him out there. But we've done everything to one side. Well, he's done everything to one side, which kind of segues me into what I usually do. And both of these methods are completely valid. But I'm going to start over. Plus 38. And I'm going to ignore that 38 and concern myself only with what I need to do to create a perfect square trinomial. I'm going to, I don't want to get rid of it, but I'm going to ignore it. What can I add to the right-hand side of this equation? I don't want to mess with the left-hand side, as I've said. What can I add to it, but also maintain the same value? What is the one thing that you can add to an equation that doesn't change it?
0.
So I'm going to do that. And you don't have to do this every time, but I'm going to add 0 to this equation. But 0 has lots of different forms. And I conveniently want my form to be plus 36 minus 36 plus 38.
That's still 0.
That's still 0. I haven't changed the right-hand side, which is the goal when dealing with a function. Equations, you can change both sides. Functions, we need to keep that left-hand side f of x. We need f of x to just always be there. Otherwise, we'd be graphing a different function. And then now I'm at I'm just going to jump to this is what you've written, x minus, my computer's slowing down a little bit, x minus 6 squared. And then that is the plus 2. Your way's better in terms of efficiency.
But it also takes a little bit of like, okay, how can I make 38 into 36?
Yeah. And imagine if you had fractions. It's doable.
Doable.
All the power to you and your brain to handle fractions in your head. But I like to just put all the stuff on the page and then instead of having to think backwards, I like to just think forwards. Both of these methods are valid. And I would say from no data set at all, I would say half people do the first one and half people do the second one.
Wow.
Maybe
we should actually collect some data.
Yeah, let's see what people like to do. Now we're in parent function form though. I call it parent function form. What do we call it? Vertex form.
Vertex form.
All right, vertex is
6 2.
6 2. Those negatives will get you.
Yeah.
My dad used to say, if it's a snake, it would have bit you.
Okay.
I'll add that this is upward opening upward.
Mm-hmm.
I like to get maybe that many points. I think that's an appropriate amount of points before I just start to sketch it.
Like you don't want to just do it with the two that are right there, because then it can very dangerously turn into like an absolute value.
Yeah. This adds that what we call concavity.
Concavity. You know what I like to talk about with concavity? Spoons.
Spoons.
I staged a spoon next to my teaching setup.
Just in case you need to talk about concavity, because it'd be terrible if that spoon opened down.
Yeah, because then like how can you eat stuff? It'd be really
exactly.
sad.
Cavity is the way a curve curves, whether it's curving upward or downward. It's not what you get when you forget to brush your teeth. Yeah. All right, domain, let's just knock this out. But maybe we can do it without even looking at the graph. It's a parabola.
Domain, all real numbers.
Range.
It's going from the vertex up, so to the infinity. Increasing from where our vertex is to infinity. So 6 to infinity. Decreasing from negative infinity to our vertex, which is 6. Are you okay?
Yeah, I'm struggling real hard.
I can help you write if you want.
You want to finish this out for me so I can take a second to catch my breath?
All right, so we have x-intercepts of none, so not applicable because our vertex is above where our x-axis is. Mm-hmm. Our y-intercepts are where our function evaluated at 0 is. So what's that? 36. Oh, plus 2, which is 38, and that was something that we had from before.
Can you rewind real quick and talk about that? Sometimes vertex form is not the best form. Each of those forms that we talked about before have their purpose. Let's look at them real quick. They're up here. Like standard form, I think we just established a very powerful use of standard form. What does standard form immediately tell you?
Your y-intercept.
Yeah, right. Because when you plug in 0, everything goes away except for the c. What does factored form tell us?
Where our roots are.
That's why I use R1 and R2. I don't think we mentioned that.
Oh, nice, clever.
And then vertex form tells us our vertex. So all the forms have their purpose, and the form that we had been given at the beginning gives us a 38. That's nice.
Very nice. Do we establish we want 38 there, or do we want a point?
Let's put a point. I think that it's implying that it's what is the y-intercept? At what coordinate does the graph cross the y-axis? I think that's a point. I don't know. That's an opinion. That's
fair. There's no asymptotes because it's a parabola. And is it bounded? Yes, it's bounded below. It's bounded below, not bounded. And behavior, we're going to infinities. And extrema. What do we have? It was a absolute min because we have an upward facing parabola. And our absolute min is 2.
Ooh, that was fun. I just strolled up to look at the graph again. which is what's being recorded. I strolled back down, and absolute min was there. So I went up. You said something. I went back down, and it was there. It was magic. It was not technology. That was magic. Okay,
Sure.
cool. Let's proceed. We are now down here at 2x squared plus 6x plus 7. This one differs. Just like our last problem with Mr. Ostrander differed. We have a coefficient. I think he learned that vocabulary the other day. Of 2. What do we do?
Well, I think it would be nice if we could just factor out the 2 and just not deal with it right now.
You want to do that? Or do you want me to write it?
Helpful. Oh, sure. I can write it.
Okay, cool.
2 x squared plus, and then when we factor 2 out of 6, what do we get?
You got a 3x.
Okay. 3x, and I'm just going to leave a little gap. And then we have plus 7. So what do we need to make inside the parentheses into a perfect square trinomial, Mr. Kirk?
All right, so I like that you moved that 7 out. I don't want to deal with that 7. I don't want to think about turning that 7 into a different number. Just leave the 7 on the side. Because now I can look at this x squared plus 3x. I want to look at b. B is 3. I want to divide that by 2. Because I need something that adds, something that when I add it to itself, I get 3, which is that number divided by 2 by definition. 3 halves. And I very much appreciate that you wrote fractions because I don't want to deal with 1.5 squared. Because 3 halves squared for me is much easier. I know my exponent rules. So I think we want 3 halves squared. We want that b divided by 2 squared.
And that's a plus, right?
And that's a plus. And I think it's always going to be a plus, right?
Yeah, because when we're having, whenever we have negative times negative, we get a positive. So that last term is always going to be positive, even if we have negative in the middle as our b. Or b over 2 is negative. Cool. Okay.
How do you draw a crab? Look, it's a blue crab.
Oh, that's funny. I made the body of the crab a little more hexagonal because, like if you've ever eaten crabs, you know that it's a hexagon.
Can this be our class mascot?
Krabby, the precalculus crab.
Krabby the precalculus crab. Yep.
It's grumpy because it doesn't know about.
Is that a Pokemon reference?
No.
It wasn't.
It was a reference to Rady the math cat. Have you ever watched that video?
No.
It's hilarious.
At University of Maryland.
Creepy.
At University of Maryland, we had a math duck. Do you remember walking by the math lounge and seeing a duck in the window? It was about this big. No? Okay.
No. I thought that was in the physics lounge.
The physics people steal the math duck?
Oh.
There was a feud between the two groups. Anyways.
Yeah. So we have 2, and then this is a perfect square trinomial of x.
Now 3 halves is our b, right?
3 halves is our b. What do you mean our b?
Well, so when we factor, we don't really need to actually factor this thing. We've set ourselves up to factor it. When we have x squared plus 3x plus 9/4, you don't have to think about how to factor that because it's always going to be that thing that you squared as your b value, this thing. Am I making any sense?
Okay, yeah. Mm-hmm.
Okay.
But we just kind of broke math a little bit because we just put in something and we didn't take it away. So what do we need to take away so that we're actually adding 0?
3 halves, right?
Well, 3 halves squared, but then we're also like
so 9/4.
But then there's that 2 hanging out.
Ooh. Yeah, if we look at our equation, that 2, we added 9 halves, 9/4 inside these parentheses that are being affected by that 2. I think we need to subtract 2 times 9/4. 2 times 3 halves squared.
Okay. So then we're subtracting, what is this actually? What, 9 halves? Okay.
All right, so now we need to do a little bit of fraction stuff. That's 14 halves minus 9 halves. That's 5 halves.
Okay. And then what do we have? Man, that's like frustratingly laggy.
It is what it is. I think you told me something that was wise, and that was when technology does something that you don't like, either you fix it or you live with it, because life isn't going to, what were the words you used? Bend to your will.
Is that what I said?
I don't think it's what you said,
Just
but I'm
like,
paraphrasing intensely.
You just move on. It's okay.
Yeah. Okay. Yeah. It's not perfect, but let's live with it.
Yeah.
All right, there we go. Can you do me one favor? Can you add f of x in front of that thing?
I can.
I just want to remind everyone that we never messed with the left-hand side of this equation, this function. Because if we did, we'd be changing the function. We don't want to change the function. Everything we did was additive identity. We added 0 to the right-hand side, which is valid in math. Also multiplying by 1, but we didn't do that. All right, I think we can do this. I think we can get this domain all the way down to extrema without graphing it. I believe the question prompts.
But it says a sketch might help. Can we do a sketch?
Yeah, we can do a sketch. Can I do it on the side?
Yeah.
Sweet. So I'm thinking in my head, we have the vertex is -3 halves, comma 5 halves.
Mm-hmm.
I'm going to give my graph like that.
Oh, nice.
-3 halves, comma 5 halves. I'm just going to say that this point is -3 halves, comma 5 halves. All right, and then it's a sketch, right?
And so you just do a upward facing parabola that vaguely looks like it's dilated.
Yeah, it'll be a little bit more narrow than your normal parabola. Yeah. But I think that'll do everything that we need it to do.
I think
except for one thing, but we have a solution to that. Right.
Okay.
That's the y-intercept.
Oh.
We currently do not know what the y-intercept is, but can you just tell me it within the next 3 seconds what the y-intercept is?
Well, I think it's 7 because of our original prompt.
Plug in 0, you get 7. Let's go ahead and add that. 0, comma 7.
Solid.
All right. Once again, we do not have x-intercepts. We have not picked the best problems.
Or we're just normalizing that it's okay to not have not applicable for things.
But I believe you've described how to find the x-intercepts.
We just look for the roots.
Right. Yeah. Either factor or set equal to 0. 0 equals function. Solve that. That might involve factoring. Yeah.
It might involve, usually, unless it doesn't.
All of our examples today did not address this issue, though. Some of them will in the. We'll make sure some do in the practice set. All right, domain. I'm going to take this one. You did the other two. All real numbers. It's a parabola. Range. 5 halves to infinity, including 5 halves. Increasing. 5 halves to infinity. Decreasing -infinity to -3 halves. All right, asymptotes. I know that these questions can get redundant in class, but we just want you thinking about these terms constantly. We want them to become part of your vocabulary, and you need to use terms to get used to the vocabulary. I think the best way to learn a language is to immerse yourself in that language. I think that's something that's often said. Or we're trying to immerse you in these vocabulary terms. So I know that this can be the language of math. Asymptotes, none. Bounded, bounded below. All right, while all of these answers are very similar in the previous 2 examples in this, we just want you reading these and using them and thinking about them. And behavior, I believe it's still infinity and infinity. I'm getting better at writing that infinity symbol, by the way. Oh, you got me with the crab. You were waiting for it. I need to get better at drawing my crabs because that's a phenomenal crab.
Oh, thank you. Thank you.
And it's hexagonal. It's so mathy. I love it. Maybe we should make everything about it like mathy. Like the claws should be like trying. I don't know.
Oh, yeah, but they're concave up.
Concave, yeah. And the extrema, I believe our value was 5 halves is a absolute min. And I guess I'm going to do this. We didn't do this before. It's okay if you don't. But I'm going to write absolute slash relative, right? It by definition meets the definition of relative min, right?
It does.
Yeah. Do you think that's confusing if I'm calling it both?
It's okay.
Okay. Let's proceed. We got one last thing for you. We've done... Let me scroll back up. We did a problem that was already in the form. We then did a problem where we had to put it into the form, but we did not have to deal with a coefficient. a leading coefficient, non-1. Then we dealt with when the leading coefficient was non-1, not 1. My language is not the best right now. What if it is any number? A, B, and C, where A, B, and C are real numbers. What do we do? And we think that the best way to do this problem is concurrently with a very difficult version of number 3. Negative 2x squared minus 5x plus 9. Those numbers are nasty. A, B, and C are any number. We're going to do these together.
Sounds good. Are we skipping the Brahmagupta quote?
We don't have to skip the Brahmagupta quote. I was actually going to show it back up so it was visible.
Okay. Cool.
Do you want to read it?
Sure. 2 the absolute number multiplied by 4 times the coefficient of the square, add the square of the coefficient of the middle term. The square root of the same less the coefficient of the middle term being divided by twice the coefficient of the square is the value.
What could that mean? Let's leave that there for a second, and we'll come back to it at the end. All right, let's do this thing. So we determined beforehand that I would work on the left-hand side while you work on the right-hand side?
Yep.
Cool. All right, so I'm looking at this thing. We got negative 2x minus 5x plus 9, and I'm thinking about what you did earlier. You factored that negative 2 out first. So that's what I'm going to do. Negative 2 times x squared. I need to factor it out of the negative 5, so I believe I'm going to get a plus 5 halves x plus 9 on the side. I'm not going to factor it out of the 9. I'm going to double check real quick that negative 2 times 5 halves is negative 5, and it is. Right? Whenever I'm worried about my answer being wrong, I can just double check that it gives me what I originally had. And I have factored out my negative 2. I left a little space to add that special number.
And then what I did was factor out the a and leave the space. So we have x squared because ax, when you factor out a, is just x squared. And then b over ax, because when you have b and you factor out a, you get b over a. And then plus c, I didn't change anything.
Yeah, that's what we want to do. All right, so now I'm looking at mine. We're dealing with fractions, but you're dealing with fractions too, so we're kind of in the same boat. I'm going to add b divided by 2 squared. So b here for me is 5 halves. So b divided by 2 squared, I believe, is 25 fourths. 25 fourths. Oh, no, I think I made a mistake. B divided by 2 is 5 halves divided by 2. 5 fourths squared is 25 sixteenths. Let me fix that in my problem. All right, mistakes are okay. Hopefully,
mistakes are okay.
You have someone with you to catch it. All right, and your life is almost easier. You're just b divided by 2, b divided by 2a squared.
Right, I'm just leaving it alone.
Oh, but you're better than me because you already. I'm actually going to erase this stuff because I want that room.
Okay, I subtracted out.
Yeah, you're one step ahead of me.
Okay.
So
negative 2. I almost forgot it earlier.
X squared plus 5 halves x plus 25 sixteenths. Factoring this will be easy. Plus 9 minus. Oh, wait, not minus. Plus, because I have negative 2 times 25 sixteenths. I have subtracted 25 eighths. So I need to add 25 eighths to my problem. And then what did you do?
Well, I subtracted because I have, man, I really want to point. So I subtracted because my coefficient a is taken as like the value a. So I'm just taking away the that opposite. Oh, cool, thanks.
All right. So now what do I need to do? I need to factor, right? That's what we set ourselves up to do.
Mm-hmm.
And I'm only going to do one step. I'm just going to do the factoring so we don't get too much in one step. But if I factor this thing, I'm going to have 5 fourths quantity squared. 5 fourths was the thing that gave me 25 sixteenths. And I'm still going to have plus 9 plus 25/8. We'll do that in the next step.
Okay. So I'll have C minus, and I guess I should multiply this out. So we have what? B squared over 4A.
I think so,
because
yeah.
we have A over A squared. So that'll just be 1A in the denominator. Okay.
Cool. All right, because I think the combining fractions is an activity in its own right. I'm going to slow down a little bit. All right, so I'm going to now do that exactly. -2 x plus 5/4 quantity squared. 9 plus 25/8. I need eighths. That's going to be 72/8. That's 9 plus 25/8. And I'm just going to go ahead and add them. Is that okay?
Sure.
72, 77, 87, 97. 97/8. And I believe 97 is prime, so I am in my simplest form. What happens when you add your two fractions?
Well, so I'm just going to make a common denominator by multiplying by 1 of 4A over 4A. In the previous step, I just showed that. But then we're going to have 4AC minus B squared over a common denominator of 4A. So we are 4Aing into the future.
I'm going to throw my f of x's here. You kept the g of x. You're better than me.
Well, I was listening to the feedback that I got before and then remembered.
And I did not listen to the feedback that I gave. All right, we're here. I think we're there, right? We have our vertex form.
All right, cool.
All right, so my vertex is at negative. I'm going to write this down. My vertex is at -5/4, comma 97/8. That's nasty, but we're trying to do this for any possible quadratic.
So my vertex is what? Negative B over 2A, comma 4AC minus B squared over 4A.
Boom. Not too shabby.
Right.
I think this says something powerful, though. Negative B over 2A. Are you telling me that given a quadratic in standard form, ax squared plus bx plus c, without doing any work, I can immediately know where the vertex is horizontally? Just by taking...
I would say it's not like no work, because I would say that, negating something, dividing by 2 times something else, like that's like a couple of operations.
It is a couple of, but
no work.
Without doing all of this, I can just look at this and be like, negative b divided by 2a. That's the vertex, the x coordinate of my vertex.
Yeah, that's not too bad.
And that's what I got, right? Yeah. That's actually going to be really useful when we look at optimization problems in the future. Because knowing simply where the vertex is horizontally can be really powerful. Because the parabola is symmetric. And it can tell us a lot about the graph simply knowing where our axis of symmetry is.
Because that's usually where our either absolute maximum or absolute minimum
Max. All right, so we have one last thing that we need to do. And that is find my pen. Found it. We need to finally find those x-intercepts that we've been avoiding all of this lesson. So to find my x-intercepts, I need to set this thing equal to 0. I'm going to scroll down a little bit. Give myself some room. Also, so we can see what you've written over here. 0 equals -2 times x plus 5/4 squared plus 97/8.
97/8? Oh my goodness.
Well, yours is more ridiculous. 4ac minus b squared over 4a.
That's true.
Are you setting yours equal to 0?
I'm trying to move it, but I guess because I was thinking I could like match where you were horizontally, but I can't. So I'm just going to draw an arrow and then 0.
Nice. I can match you horizontally.
It's cool.
We want them at like the same level at the end. So I'll meet you. I'll find my way to the same elevation as you on the page.
Oh, you'll do a stretch.
Yeah. Are you writing yours?
I am.
It's that magic. Oh, boom.
Boom.
Boom. Party time. Excellent.
Woo, woo,
It's a Wayne's World reference.
I didn't get it.
Do you think anyone gets it? Wayne's World?
I don't know.
Mm-hmm. All right.
I was gonna do like that.
I used to have a soundboard on my phone that I'd hold around in class. Whenever a kid got it right, it'd be like excellent, or made people so uncomfortable. All right.
Yeah.
Let's solve for 0.
That made me uncomfortable just now. You're just like making those sounds.
Minus
All right.
97/8. Minus 97/8. I'm making my way down to your level. That sounded mean.
It's okay.
-2. X plus 5/4 squared. So now we're like in Mr. Ostrander land, where we're like using the complete of the square to solve.
Oh, Mr. Ostrander land.
Boom. Every time yours drops, you got to be like, boom. My equation drop.
Okay.
Divide by 2. 97/16.
Divide by a. So I'll multiply by 1 over a over here, just because it's easier. Boom.
Nice.
And then
square root both sides.
Zoom, but it's, I guess, delayed. Canceling.
Ooh, mine is a nice little 4 there. X plus 5/4. Ooh, I forgot my plus or minus.
I'm going to change this order around. B squared minus, and then the 4 in AC, because of the commutative property of
addition, right? Okay. As long as of addition, not subtraction. Subtraction does not have a commutative property, but addition, including negative numbers, does.
But if you think of addition, or if you think of subtraction as addition with a negative, boom.
Boom. And that's why subtraction doesn't exist and division doesn't exist. I'm going to go ahead and add another page here so that we can write our final answers here in big letters at the bottom. I need to authorize Google. Oh, no.
Oh, my goodness. So many email accounts.
I know. Now everyone's going to be like sending emails to I'm going to have to cut this part out. 14,000 people using Kami. That's why it's so slow. All right.
There's no way. 14,000?
Oh, this is the work that we did with Mr. Ostrander. We're going to have to start a new page.
I think we did insert another page.
930, 14,000. All right. So let's just come back here. And
it's not showing up for me.
Maybe you need to refresh. We are learning how to collaborate on a Kami. So do you have no new page?
Oh, I have lots of pages now. I'm on page 7 now.
Sweet. That's where we're gonna. I think we need to take this.
On page 7.
So I have negative 90 root 97 over 4 is equal to x plus. Oh, nice. That's one more.
That's where I am.
So I have negative plus or minus root 97 over 4 is equal to x plus 5/4. That's where I am.
Okay, and then I have b squared minus 4ac over 4a squared, and then I need the square root of that, plus or minus with my, nope, what was it, x plus b over 2a, which was...
Boom. You're on fire algebraically.
Oh, thank you. Okay.
All right. I think we're one step away. Maybe 2.
Oh, wait. I can change my denominator.
All right.
Which you did in one step, but
Yeah, you can. You can.
Yeah, because 4a squared is 2a quantity squared. So it can get broken out of radical jail.
I need to use that one. I like that.
And then we have x plus b over 2a. Bam.
Boom. All right. Let's subtract these things and get that x. X is equal to, for me, negative 5/4 plus or minus root 97 over 4. And I'm going to go ahead and combine those in my final line. Negative 5 plus or minus the square root of 97 over 4. Put a big box around my answer while we wait for you to equation drop.
Equation dropping. Bam. I think that's right.
That looks familiar.
Oh. This I feel a song coming on. I think we need to pick up
I don't know
that
how to
song.
sing it. Da 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 da. We're getting copyright infringement. We're gonna get a.
Not if we sing it out of tune.
I don't know how to sing it though.
X equals negative b.
Oh boy, we're not gonna sing it. Let's stroll up real quick and revisit what Brahmagupta said 1,500 years ago. To the absolute number multiplied by 4 times the coefficient. So the absolute number in the standard form, that's like C. Multiplied by 4 times the coefficient of the square, A. All right. Add the square of the coefficient of the middle term. I think the absolute here is referring to the minus sign. I think. All right, so B squared minus 4AC. The square root of the same, less the coefficient of the middle term, minus B. I'll put that minus B in the front. Divided by twice the coefficient of the square value. Boom. 1,500 years ago, this formula was established to find the roots of quadratics. And if I take out my history of math book, I need to find the chapter that talks about it, but that was one of the major motivators for math 1,500 years ago, was trying to solve the quadratic equation. Sounds like a journal idea.
That does sound like a journal idea.
Yeah.
And it was also really helpful in like solving differential equations in order to, do the math necessary to get us to the moon and all that stuff. And
I think people have talked about that already in the journals. All right, there you go.
Look at eigenvalues if you want to get like really excited about the quadratic formula.
You'll be ready for Mrs. Contreras' linear algebra class
in like 3 years.
Yeah, 3 years. There you have it, though. The quadratic formula. We're going to finish this video with that. Well, actually, no, we're not going to finish this video with that. We are going to finish this video with an icebreaker. You want to introduce the icebreaker? If
you could have any superpower, what would it be and why?
What would it be and why? Can you go first?
While you're thinking, I can totally go first because I've thought about this a lot. I would want to be able to handle like really hot objects so that when I'm cooking, like on a comal or something, and I'm like flipping things over, I'm like not afraid.
I was making rice last night and I touched my rice pot with my hand and it like burnt my hand pretty bad. That would be a useful.
Do you use a rice cooker or do you cook rice on the stove?
Rice cooker.
Okay.
Wait, we have to go back to the topic. My power, and I'm only saying this because I haven't thought about it as long as you. I might change my mind in the future. You have to give me that permission.
That's totally fine.
But right now, just off the top of my head, my favorite superhero is Superman. My favorite superhero is Superman. One of my favorite TV shows is Smallville. Flying, I think, would be my answer right now. Because I don't want a power that like is going to. I don't need a power to like defeat people. People say like, oh, like invisibility is the best because you can deceive people, or like all these different powers so you can beat other people up and stuff like that. I'm like, I don't want that. I don't need to be super strong to be happy. But I think flying would make me really happy. Maybe teleportation, actually. Because then I can like teleport to Chipotle right now.
And get like all the burritos.
And get all the burritos.
Double burritos.
The double burrito we talked about in that last video. That is a wonderful tie-in. It's like we're like a podcast. I think teleportation. Teleportation is my answer, so I can be anywhere I need to be, and I can be that far away from a Chipotle burrito if necessary.
You still have to wait in line at Chipotle, though.
No, I'm going to teleport to the front of the line.
That's rude.
I mean...
I think that's an abusive power.
Yeah, you're right. I just said that I don't want power to be... to cause harm to other people. Yeah, you're right. So I teleport to the back of the line.
All right, that's fair.
And I'd wait my turn.
That's good.
All right, there we go. Let's close this one out. Let's stop the share before we do it. We've learned our lesson.
Yep.